Welcome to Grandpa's Late Nights. It's good to have you here, kiddo. Wherever you are right now, whatever corner of the world you've curled up in tonight, I'm glad you found your way to the porch. Maybe you're under a heavy blanket with the window cracked just enough to hear the wind. Maybe you're on a couch that's seen better days, or a train rocking gently through the dark, or a bed that's a little too far from home. Doesn't matter. You're here now, and that's enough. Settle in. Let your shoulders drop a little. There's no hurry tonight. There never is on this porch. And before we get going, let me just say a quiet thank you to those of you who've sat with me before, night after night. Thank you, truly. It means more than you know to an old man with a story and a porch light. And if you're new, if this is your first time drifting off out here with me, well, welcome. If you'd like more nights like this one, a little like and a subscribe helps this sleepy little channel keep its lights on. Small creators like me really do lean on it. But no pressure, kiddo, none at all. You don't owe me a thing. Just rest. Now, I should warn you, tonight's story is a big one. Maybe the biggest there is, and I'll do my best to tell it slow and soft, the way you'd tell a bedtime story to someone you love. But I have to be honest with you. It's the kind of story that might be a little too interesting to sleep through. So here's our deal. If you drift off before the end, that's perfectly fine. The stars will still be there when you wake. The ideas aren't going anywhere. But if you find yourself still awake at the end of it, well, at least you'll have learned something true and strange about the sky you sleep under. A fair trade, I'd say. Let me start with something, and I want you to just let it wash over you. Don't try to hold on to it too tight. Right now, somewhere out in the dark above your roof, there is light traveling toward you. Light that left a galaxy a very long time ago. Millions and millions of years before you were born, before anyone was born, before there were eyes anywhere to see it. That light has been crossing the emptiness ever since. Patient, steady, falling through the black at the only speed it knows. And it is coming, in a sense, for you. And it will never arrive. Not late, not someday, never. That light is already on a journey that has no ending where you are. The galaxy it came from is, for all the meaning the word can carry, already gone, lost. Not because it burned out, not because it wandered off somewhere, but because the space between you and it is stretching, growing, opening up faster than the light can ever close it. The light is swimming as hard as it can toward you, and the river underneath it is flowing the other way, and the river is winning. It always will. That's what I want to tell you about tonight, kiddo. Not how big the universe is. You've probably heard that part 100 times. I want to tell you something quieter and stranger and a little bit sad. I want to tell you that there is a part of the universe we have already lost. Not might lose, not could lose someday, way out in some far-off future. Already, right now. Tonight, while you're lying there getting heavy-eyed, the door is closing on pieces of the cosmos that we will never, ever reach again. This is the work of a man named Abraham Loeb, an astronomer up at Harvard, who sat down a couple of decades back and did the math on the long, long future of the sky. And what he found is one of the loneliest, most beautiful truths I know. He showed that the number of galaxies we will ever be able to see, ever in all of time, stretching out forever in front of us, is a finite number. There's a limit. There's a wall around what we can touch. And we are already pressed right up against most of it. So let me give you the part that always stops me cold, even now, even as old as I am. Imagine you could leave tonight, right out of that bed, And imagine you could travel not in a car, not in a rocket, but at the very fastest speed the universe allows, the speed of light itself, the speed of the light from those distant galaxies. Nothing in all of creation moves faster. You'd be the swiftest thing there is. And even then, even moving at the absolute limit of what's possible. Do you know how much of the universe you could ever reach? How many of all those galaxies scattered across the sky tonight you could ever actually get to, or even send a single whispered signal to? About 3%. 3. Out of 100, even at the speed of light, even with all the time in the world, even forever, you could only ever touch about 3 of every 100 galaxies you can see. The other 97 are already beyond you, already past the line. You can see their light, the light they sent long ago, and that's a kind of gift. But you could chase them for eternity and never close the distance. They're like ships that left the harbor before you were born, already over the horizon, and the sea between you keeps widening. I know. That's a heavy thing to set down in front of you, right as you're trying to fall asleep. So let me take it slow now, and let me unbraid it for you, gently, one strand at a time. Because the strange thing, as the comforting thing in its own odd way, is that none of this is a tragedy. Nothing is breaking. Nothing's going wrong. This is just how the universe is built. And there's a deep and quiet beauty in understanding the shape of it. So let's wander into it together the way we always do. No rush. We've got all night. Let me start where most folks start, because it's the part you've probably heard, and we should get it out of the way nice and slow before we get to the deeper, stranger stuff. You've maybe been told that the universe is about 13.8 billion years old, and that's true. About as true as we can measure it. The number, if you want the careful version, is 13.787 billion years, give or take 20 million either way. That comes from a spacecraft called Planck, which spent years drinking in the faint glow of the early cosmos and reading it like the rings of an ancient tree. 13.8 billion years since the beginning. That's how long there's been a universe at all. Now here's the little riddle that everybody loves to serve up. And I'll give it to you too, because it really is a good one. If the universe is only 13.8 billion years old and nothing can travel faster than light, then it would seem the very farthest we could ever see is 13.8 billion light years in any direction. Light's had 13.8 billion years to travel, so it could only have crossed 13.8 billion light years of road to get to us. Makes sense, doesn't it? Simple. Except it's wrong. Or rather, it's not the whole story, not by a long way, because the part of the universe we can actually see, the observable universe as the astronomers call it, isn't 13.8 billion light years across. It's about 93 billion light years across, 93. Side to side, from here to the farthest edge in one direction is about 46.5 billion light years, and the same again the other way. And that gives you 93 across the whole thing. And I can almost feel you doing the arithmetic in the dark, getting tangled. How? How can we see something 46 billion light years away if the universe has only existed for 13.8 billion years? How did the light cross all that road in so little time? It didn't go faster than light. We just said nothing can. Here's the thing, kiddo, and this is the first real key I want to hand you tonight. The light didn't have to cross all that road. The road grew. Let me give you a picture for it, the kind you can hold without thinking too hard. Imagine an ant, a slow, patient little ant, walking across a long sheet of rubber toward you. The ant walks at its one steady speed. It never speeds up. But while it's walking, somebody takes hold of the rubber and slowly, gently stretches it. Stretches it the whole time the ant is crossing. So the ant takes its little steps, and underneath those steps the rubber is widening, and by the time the ant finally reaches you, the place it started from has been carried much, much farther away than it was when it set off. The ant is light, the rubber is space itself. And that's the secret the whole night sky is built on. Space is not a fixed, empty stage where things move around. Space stretches. It has been stretching this entire time, all 13.8 billion years of it. So when light set out from some far galaxy long ago, that galaxy was actually fairly close. The light didn't have far to go back then, but as it traveled, the space underneath it kept on growing, kept on stretching, carrying the starting point farther and farther back. The light arrives at last, having traveled for billions of years, but the place it came from is now much, much farther away than the distance the light actually covered. That's how a 13.8 billion-year-old universe ends up 93 billion light-years wide, not because anything broke the speed limit, but because the very ground beneath the light kept opening up while the light was crossing it. This is the careful work of cosmologists like Charles Lineweaver and Tamara Davis, two people who've spent a good part of their lives gently untangling exactly these knots for the rest of us, because heaven knows they get tangled easily. 46.5 billion light-years out in every direction, 93 across, a universe far wider than its own age would suggest, all because space itself is a thing that grows. Sit with that one a moment. There's no need to grasp every piece of it. Just let the shape of it settle over you like a blanket. The road grew while the traveller walked. That's all it is. That's the whole trick. Now, there's an edge to what we can see, that 46.5 billion light-year line in every direction. And I want to be careful here because in a little while I'm going to tell you that the edge isn't really a wall at all, and that there's more than one kind of edge, and that the one that truly matters is a different one entirely. But that's later. For now, let's talk about the farthest thing we can actually see, because it's a wall of a kind, and it's a beautiful one. When you look out as far as your instruments will let you, out toward that edge, you eventually run into something. Not a galaxy, not a star, a glow, a soft, even ancient light that fills the whole sky in every direction you point. The astronomers call it the cosmic microwave background, and it is the oldest light there is, the oldest light there can be. Let me tell you where it comes from, slowly, because it's one of the gentlest stories the universe has to offer. When the universe was very young, it was not the calm, dark place you see when you look up tonight. It was hot, unimaginably hot, and bright, and thick, so thick that light couldn't even travel through it. The whole cosmos was a kind of glowing fog. A fog made of bare particles, so crowded and so charged that any light trying to cross it got knocked about and scattered before it could go anywhere. The way a flashlight beam gets lost and smeared inside a thick bank of mist. You couldn't have seen your hand in front of your face if there'd been a face, if there'd been a hand. Just glowing fog everywhere, all at once. And then the universe did what all hot things do given time. It cooled. Slowly, slowly. And there came a moment, about 380,000 years after the very beginning, when it had cooled just enough. The fog cleared. The bare particles came together into the first calm, settled atoms, and all at once the universe became transparent. The mist lifted, and for the first time in all of history, light could fly free. It could cross the whole of space without being knocked about. That light, the light set loose the moment the fog cleared, 380,000 years in, has been flying ever since, for 13.8 billion years. And it is still arriving, right now, tonight, from every direction in the sky. Stretched and cooled and softened by all that traveling, by all that growing road beneath it, until it's no longer a blinding glow, but a faint, gentle warmth. A whisper of the fire that once filled everything. That's the cosmic microwave background, the afterglow of the morning of the world. And here's why it matters for our story. It is a wall, not a wall of stone or distance, but a wall of fog. We cannot see past it, not with light anyway, because before that moment the universe was opaque. There's nothing for our eyes to find back there but the fog itself. Try to look earlier than 380,000 years, and you simply run into the glow the same way you can't see through the surface of a cloud, no matter how hard you squint. The light from before that time is trapped inside the mist forever. So this oldest light is, in a very real sense, the farthest thing we can ever see. The curtain at the back of the visible stage. Now, the folks who measure these things have a way of describing just how stretched that ancient light has gotten on its long, long journey to us. They talk about something called redshift. And it's a simpler idea than it sounds, so let me hand it to you plainly. You know how a train whistle drops in pitch as the train rushes away from you, how the sound seems to stretch out and sag and go lower the moment it's heading off into the distance. Light does something a little like that. When the thing giving off the light is moving away from you, or when the space between you and it is stretching, which amounts to much the same, the light gets stretched too. Its waves get pulled longer, and longer light for the colors we see means redder light. So we say the light is redshifted, pulled toward the red end, stretched out by the journey and by the growing of the road. That ancient afterglow, the cosmic microwave background, it has been stretched an enormous amount. The astronomers put a number on it. They say its redshift is around 1100, which is just a way of saying its light has been stretched to about 1100 times longer than it was when it first set out. Stretched so far that it's left visible light behind entirely and become that faint, cool whisper of warmth we can only catch with special instruments. 1100. That's how much road has grown beneath that oldest light. That's how far it's come and how much the journey has worn it down. And I'll tell you, kiddo, there's something tender in that if you let yourself feel it. The oldest light in all of creation arrives at your door tonight, not as a blaze, but as a hush. Worn soft by 13 billion years of traveling. The first light there ever was, knocking gently, gently on the roof above your bed. And we can read it. We can listen to that whisper and learn from it the age of everything, the shape of everything. It's how we know that number, 13.8 billion years. We learned it by listening to the oldest light in the world, the way you might learn a man's whole life by the lines in his face. So that's where we are, settled down out here on the porch. We've got a universe 13.8 billion years old. We've got a visible piece of it about 93 billion light years across, far wider than its age would suggest, because the road itself keeps growing beneath the traveling light. And we've got that ancient wall of fog at the very back of it, the oldest light there is, stretched 1100 times over, arriving as a soft, warm whisper from the morning of the world. That's the part most folks tell you. That's the appetizer, as they say. The universe is big, it's old, and there's a wall we can't see past. And if that were the whole of it, it would already be a fine and humbling thing to fall asleep on. But it isn't the whole of it. Not even close. Because everything I've just told you treats that edge like a wall, a fixed thing, a far boundary, just too distant to have reached us yet. And kiddo, that's the part where nearly everyone goes wrong. That's the misunderstanding I want to take you past tonight, soft and slow, because the edge of the universe is not a wall, it's a horizon. And those are very different things. A wall is a wall, it stays put. You could walk up to it, lay your hand on it, walk along it, but a horizon isn't a place at all. It's a line drawn by how far light can travel and how the space beneath it behaves. And here's the part that ought to make you sit up if you weren't already getting so pleasantly heavy in the eyes. There isn't just one of these horizons, there are several. Several different edges to the universe, and almost everyone, in almost every telling, mashes them all together into one and calls it the edge. But they're not the same. They mean different things. Some of them are still gently growing. And one of them, the one that truly matters, the one this whole story turns on, is closing in. That's where we're going next, you and I. Into the difference between an edge that's too far to have reached us yet, and an edge that we can never, ever cross. Between something simply distant and something genuinely lost. And once you can feel the difference between those two, the whole sky will look a little different to you. A little stranger, a little more precious, but we'll get there slow. We always do. For now, just rest with what we've laid down. The road grows beneath the light. The oldest light arrives as a whisper. The universe is wider than its years. There's no need to hold all of it. Let the easy parts stay, and let the rest drift off like smoke. I'll still be here. The story will still be here. And so will the light that's coming toward you tonight. Most of it anyway. Falling through the dark above your roof, patient as ever, crossing the long black road to reach you. So let me ease us toward the deeper water now, gently, the way the tide comes in when you're not quite watching it. Let me start with the one number that, if you remember nothing else from tonight, will quietly change the shape of every clear sky you ever look up into again. There's a man named Abraham Loeb, an astronomer at Harvard, and back in 2002 he sat down to work out something most of us never think to ask. Not how big the universe is, not how old, but how much of it we will ever actually be able to reach. Ever. Even given all the time in the world, even if we never stopped trying. And the answer he found was small. Heartbreakingly small. Picture light, right now, leaving some distant galaxy. It set out a long time ago when that galaxy was younger and closer, and it's been falling through the dark ever since, aimed more or less in our direction. You'd think, wouldn't you, Bia, that if a thing is moving toward you and it never stops, then sooner or later it has to arrive. That's how it works down here. A ball rolled across a floor reaches the wall. A letter sent in the post turns up on the mat. Give it enough time and what's coming toward you comes. But the universe doesn't obey that gentle little rule, because while that light is crossing the dark to reach you, the dark itself is growing. The road is being stretched out underneath the traveler, faster and faster, added to in every direction all at once. And for some of those distant galaxies, the road is now lengthening quicker than the light can run along it. The light is genuinely moving toward us, and the gap is genuinely getting wider. It is walking forward on a path that is unrolling beneath its feet, faster than it can step. So it never arrives, not late, never. That light, already underway, already pointed at us, has crossed a line it cannot uncross. And from the far side of that line, nothing it carries will ever touch us again. The galaxy that sent it is, for all the purposes that will ever matter to anyone here, already gone. Not dimmed, not hidden. Gone. In the deepest sense the word can hold. We have, in the most literal way, already lost it. Sit with that for a breath, There's no alarm in it, I promise. Nothing's about to happen to you. Nothing's about to happen to the sky tonight. It's a quiet kind of loss, the kind that's been going on the whole time, softly, while we got on with our small, warm lives, but it's real. And Loeb was the one who first sat down and put a number to just how much of it there is. Now, before we go any further into that, and we will slowly, there's no rush at all, let me say a small thing the way I always do, in case you're the type to drift off on me before the end. And honestly, if you are, good. That's the whole idea. If you enjoy these long, slow nights, a gentle like and a subscribe really do help this sleepy little channel keep its porch light on. Small creators like me lean on that more than you'd think. And to those of you already here, already subscribed, already part of these late nights, thank you. Truly. So tell me, before you fade off, where in the world are you tonight? What hour has the night reached in your corner of it? I always love to picture you out there, scattered across all those time zones, all of us under the same stretching sky. And that's all the asking I'll do. From here, it's just you and me and the long dark and the slow story. If you nod off halfway through, that's perfectly fine. None of this needs holding on to. The universe will still be doing exactly what it's doing, whether you follow every word or sink down soft into the pillow somewhere in the middle. The ideas will keep. They'll be here in the morning. They've been here for billions of years already. They can wait for you. So let me give you the second number now, the one that follows close behind the first, because together they do something to a person. Loeb's work and the people who came after him. There's a thinker named Toby Ord who laid it out plainly, and others like Hale who did the careful sums. They asked the next obvious question. All right, we can't reach everything, but how much can we reach? Of all the countless galaxies you can see in a long exposure photograph, all those smudges and grains of light, every one of them an island of 100 billion suns. How many of them could we ever actually get to? If we left tonight. If we left at the speed of light itself, the fastest anything is allowed to go, and never slowed down, never turned back, just ran and ran toward them forever. The answer is about 3%. 3. Out of every 100 galaxies hanging in your sky tonight, 97 are already beyond us, not far, beyond. We could no more reach them than you could reach yesterday. Even setting out this instant, even at light's own impossible pace, even with all of time ahead of us, 97 out of 100 are sealed away on the other side of that line. We can look at them. We can photograph them, name them, study the ancient ghost light they sent us long ago. But we will never touch them, never reach them, never send so much as a single whisper their way that arrives. They are the view from a train window. Beautiful, passing, already behind us before we ever knew them. So there it is, laid quietly at your feet, the strange, true thing at the heart of tonight. The universe you can see is enormous, and the universe you can ever hope to belong to is a small, bright island in the middle of it, and the water around that island is rising, slowly, gently, but it's rising. Now, I know that's a heavy thing to set down so early, and I don't want to leave you out in that cold water without something solid under your feet. So let me back up and walk you through the gentler part, the part that almost every telling of this story does serve up, the easy appetizer before the strange main course. Because there's a question that tends to come first, and it's a good one, and answering it slowly will set the ground under everything else. The question is this. The universe is about 13.8 billion years old. We know that quite well now as 13.787 billion years. The Planck satellite worked it out, give or take a sliver. And light, that swift, unhurried traveler, covers 1 light year of distance in 1 year. That's what a light year is after all. Not a measure of time, though it sounds like one, but a measure of distance. The distance light walks in a year, so you'd reason sensibly enough that in 13.8 billion years, light can only have crossed 13.8 billion light-years of space. And so the farthest thing we could possibly see ought to be about 13.8 billion light-years away. Tidy, logical, the kind of sum you could do on the back of an envelope, except it's wrong. The observable universe, the part of it whose light has had time to reach us since the very beginning, isn't 13.8 billion light-years across. It's about 93 billion light-years across. From one edge all the way over to the other. 93 billion. In a universe that's only had 13-odd billion years to do anything at all. How? How can the thing be so much wider than its own age allows? Two astronomers, Charles Lyne-Weaver and Tamara Davis, laid this out beautifully some years back, and the answer is the same quiet trick we've already met tonight, just worn a different way. The space stretched. While the light was traveling, patiently, steadily, never speeding up, never slowing down, always at its one fixed pace, the road beneath it was lengthening. A galaxy sent its light toward us when it was, say, a few billion light-years off. The light set out, and during the long ages it spent crossing the gap itself grew, carried wider by the expansion of space, until by the time the light finally arrived, the galaxy that had sent it was no longer a few billion light-years away at all. It was 30 billion or more. The light reached us as a faint old messenger from a place that has, in the meantime, drifted impossibly far off. So the 93 billion isn't a contradiction. It's a record of how much the road grew while the runners were on it. The number doesn't measure how far light could go. It measures how far the destinations ran while the light was coming. And the very oldest of those runners, the most ancient light of all. Let me leave you with where it comes from before we go deeper, because it's a soft place to rest. There is a wall to what we can see, not a wall of stone or fire, a wall of fog. Go back far enough toward the beginning, and the whole young universe was so hot and so dense that it wasn't see-through at all. It was an opaque glow, a fog of particles too crowded for light to pass through cleanly. Light would set out and get knocked sideways before it managed a single clear stride, scattered endlessly, going nowhere. The universe in its infancy was foggy, and then, about 380,000 years after the beginning, which sounds like a long while, but against 13.8 billion years, it's the very first breath of a very long life. The universe cooled just enough. The fog lifted. The particles settled into the first calm atoms, and all at once the light could run free, straight, unscattered, for the first time. That first freed light has been traveling ever since, stretched out now, cooled and reddened by all those billions of years of growing road, until it's no longer a glow at all, but a faint, even hum of microwaves coming softly from every direction in the sky. We call it the cosmic microwave background, the oldest light there is, the light of the moment the fog cleared, and we can't see past it, not with light anyway. Try to look earlier, deeper, before that 380,000-year mark, and you only ever come up against the fog, a wall of warm haze the light itself can't get out from behind. It's redshift 1100, that wall, if you like a number to hold. The light stretched 1100 times over on its long way to your eyes tonight. The baby picture of everything, the earliest face the cosmos will ever show us. So that's the gentle part. A universe wider than its years because space grew under the light. An oldest glow arriving as a whisper from the morning the fog first cleared. Easy enough in its way once you stop fighting it. But none of that is the strange part. None of that is the loss. That's coming slow as the tide in the difference between the edges. And here is where we need to slow down a little, because what most people mean when they say the edge of the observable universe and what the universe actually has are two very different things, maybe three different things, and blurring them together, which almost every popular account does, almost every time, is exactly how you end up with the wrong picture. Not a small wrong, but the kind of wrong that makes the real strangeness invisible. So let's take it one at a time, gently, and see if we can hold all three edges in our hands at once. The first edge is the one we've already been talking about, the particle horizon. That's the technical name for it, though it sounds more forbidding than it is. The particle horizon is simply the farthest distance from which any light, or particle, or signal of any kind could possibly have reached us in the entire history of the universe. It's the boundary set by time, by how old everything is and how fast light moves and how much space has grown in the meanwhile. Right now, the particle horizon sits at a comoving distance of about 46.5 billion light-years in every direction, so roughly 93 billion light-years from one side to the other, measured as a diameter. That's the number you've probably heard before, the observable universe, 93 billion light-years across. And the particle horizon is still growing, very slowly now, adding just a thin shell of newly reachable space as time passes. Light from regions that were slightly too far away to have reached us last year is arriving this year. The observable universe is technically still getting bigger, a little bit. Every day, more of the cosmos becomes, in principle, visible to us. So that's the first edge, the particle horizon. Moving outward, still growing, the furthest anything we could ever receive from. Now that edge sounds like a wall. It sounds like a firm boundary beyond which nothing exists for us. But here's the first wrinkle, and it matters. The particle horizon is not the edge of loss. It's the edge of what has had time to reach us so far. Beyond it, right now, there is an enormous, possibly infinite universe full of galaxies we simply haven't seen yet because their light hasn't had time to travel to us. They're not gone, they're just not here yet. Not the same thing at all. The second edge is the Hubble sphere, sometimes called the Hubble radius or the Hubble volume, and this is the one that tends to break people's brains a little, in the best possible way. Ready for it? The Hubble sphere is the distance at which the expansion of space is carrying a galaxy away from us at exactly the speed of light. Right at this moment, galaxies sitting roughly 14.4 billion light-years from here are receding, are being carried away from us by the expansion of space at precisely the speed of light. And galaxies beyond that distance? They are receding faster than light. Yes, faster than light. And before your mind slides immediately to Einstein and the speed limit of the universe, let me park that thought for a moment, because we're going to come back to it very shortly, and it's important to handle it carefully. For now, just hold the strangeness. There is a sphere around us, roughly 14.4 billion light-years in radius, and beyond its surface, galaxies are retreating faster than light moves through space. That's the Hubble sphere. And then there is the third edge, the one almost nobody talks about when they describe the observable universe, the one that is actually doing the losing. This is the cosmic event horizon. The event horizon sits at a comoving distance of roughly 16 to 17 billion light-years. It doesn't sound dramatically different from the Hubble sphere, just 2 or 3 billion light-years further out. But the difference between them is the difference between a wall and a cliff. The Hubble sphere is where things are currently moving at light speed relative to us. The event horizon is something more final, more absolute. The event horizon is the boundary beyond which no event happening right now, not a flash of light, not a signal, not anything, can ever, in the entire infinite future of the universe, travel far enough to reach us. Ever. That word carries a lot of weight, so let it land for a second. There are galaxies sitting just beyond 16 billion light-years from here. Galaxies that exist right now, whose stars are burning right now, around which planets are possibly turning right now, and nothing that happens in any of them will ever be able to reach us. Not in a billion years, not in a trillion, not ever. The expansion of space between us and them is accelerating fast enough that any signal they send in our direction will simply never gain ground. It will run, and the gap will open anyway, forever. And here's the detail that turns it from abstract to physically unsettling. This event horizon is not static, it's not sitting at 16 billion light-years and waiting. Relative to the matter and galaxies of the cosmos, it is effectively contracting. Galaxies are crossing it continuously. Every day, galaxies that used to be on the reachable side of that line find themselves crossing to the other side permanently, not because they moved, because the expansion accelerated and the line moved to them. This is the machinery behind the title. This is the loss that is happening right now, tonight, while you're lying there in the quiet. Galaxies are leaving. And when a galaxy crosses the event horizon, it doesn't vanish from our sky immediately. There's something much stranger and slower that happens instead. We'll get to that in a little while. But the loss is real, and it is present tense. Tamara Davis and Charles Lineweaver wrote a paper in 2004 that they titled Expanding Confusion: Common Misconceptions of Cosmological Horizons and the Superluminal Expansion of the Universe. It's one of those papers that earns its plain, almost complaint-like title. Because the confusions they were correcting weren't fringe errors, they were pervasive, in textbooks, in popular accounts, in the work of scientists writing outside their specialty. Davis and Lineweaver laid it out carefully. The particle horizon, the Hubble sphere, and the event horizon are three distinct, separate things with different physical meanings and different futures, and collapsing them into a single, vague edge of the observable universe produces not just a simplification, but a genuinely wrong picture. So let's keep them separate. Particle horizon. What has had time to reach us? Hubble sphere, where recession currently equals the speed of light. Event horizon. What can ever reach us in all of time? Three edges, three stories, only one of them the story of loss. Now, back to those galaxies moving faster than light. Because you're allowed to wonder about that, and you're right to feel the strangeness. Everything we were taught about the speed of light says it's the universal speed limit. Nothing moves faster. And yet here we have galaxies, an enormous number of them, sitting beyond the Hubble sphere, receding from us faster than light travels. How can this be? The answer, once you have it, is clean. There is no contradiction here, no violation of relativity, no smuggled impossibility. The speed of light as a universal limit applies to motion through space. Nothing can move through space, through the fabric of the cosmos, faster than light. But what's happening to distant galaxies is not motion through space. It's the expansion of space itself. Think of it this way. Imagine you draw two dots on a balloon and then you slowly inflate the balloon. The dots aren't moving across the surface. They're sitting still relative to the rubber. But as the rubber stretches, the distance between them grows. If you inflate the balloon very quickly, the two dots can end up moving apart faster than any speed you might define for things traveling along the surface. They're not racing across the surface itself is growing. Space is doing this. Space between us and distant galaxies is expanding, not at any one point, but everywhere, a little at a time, such that the accumulated stretching across billions of light years adds up to a recession speed that can exceed c. And this is not motion through space, it's the stretching of the space itself. Einstein's limit on speed through the fabric is not violated, the fabric is just getting bigger. Now, once you understand that, the next thing that seems mysterious actually resolves very naturally. If galaxies beyond the Hubble sphere are receding faster than light, how do we see any of them at all? Think of it this way. A galaxy is sitting just beyond the Hubble sphere, say 15 billion light-years from here, receding from us at just above the speed of light. It sends out a photon in our direction. That photon, moving at light speed through space, is initially in a region of space that is expanding faster than the photon can travel. So at first, and this is the part that seems paradoxical, the photon is actually losing ground, moving toward us but being carried backward by expansion, like a person swimming upstream in a current faster than they can swim. For a while, the photon makes no progress. But here's what saves it. As the universe expands, the recession speed at any given distance changes. Expansion itself carries the photon into regions where the Hubble flow is a little slower. Closer to us, the recession speed is smaller. And eventually, if the photon started close enough, it works its way into a zone where it can finally gain ground, and then it makes it all the way to us, perhaps billions of years after it was emitted. So we receive light from galaxies that were at the moment of emission receding faster than light, because the universe's geometry is such that there's a path through which the photon can eventually escape the fast expansion zone. It takes time, enormous amounts of time, but it arrives. This is, Davis and Lineweaver take pains to explain, one of the most persistently misunderstood points in all of cosmology. People think the observable universe is the distance light could travel in the age of the universe. 13.8 billion light-years. It isn't for exactly this reason. The light can reach us from places currently 46.5 billion light-years away because those regions were much closer when the light left, and because the photon didn't have to fight the full Hubble flow the whole way. And that brings us to a distinction that matters enormously. The difference between what a galaxy looks like right now and what it looked like when the light we're receiving from it actually left. When you look at a galaxy that the numbers put at, say, 20 or 30 billion light-years from Earth, you are not seeing where it is now. You're seeing where it was when the light left it. And because space has been expanding the whole time that light was in transit, the current position of that galaxy, where it is right now, at this moment in cosmic time, is very different from where it was when its light first started this long journey toward you. The most distant galaxies we can see, the ones near the particle horizon, emitted their light when they were only a few billion light-years from where we were. That's why the light had a chance to reach us at all, but in the time since then, the expansion of space has carried those galaxies much further out. They are now in what cosmologists call their current comoving position, their present-day location adjusted for expansion, something like 30 or more billion light-years away. We're looking at an ancient snapshot of a place that has since moved. This is co-moving distance versus proper distance, and getting them mixed up is another of those confusions Davis and Lineweaver spend a lot of their paper patiently untangling. Co-moving distance is the coordinate that factors out the expansion. It tells you where something is in the cosmic grid, corrected for the fact that the grid is stretching. Proper distance is the actual distance right now at this moment if you could freeze the expansion and lay a tape measure across space. The number we usually use for the observable universe, 46.5 billion light-years, is a co-moving distance. And in this context, it's also close to the proper distance now, because we're asking about the current size of what we can observe. But when you're looking at a distant galaxy and thinking about its light's journey, you have to hold both pictures. Where was it when the light left? Where is it now? And where will it be when, if ever, we could reach it? These are three different locations, and conflating them produces the sort of confusion where people think the observable universe is only as wide as the universe is old, which it isn't, or that galaxies moving faster than light are violating physics, which they aren't. So let's hold all of this together for a moment, because it's worth pausing to feel the shape of what you now know. There's a sphere around us about 93 billion light-years across, containing everything that has had time to send light to us since the beginning. Beyond it, the universe continues, probably forever. Inside it, the particle horizon is still growing, adding thin shells of newly reachable space as time passes. The Hubble sphere, smaller at about 14.4 billion light-years, is where recession currently hits light speed. Beyond it, galaxies are retreating faster than light, but some of their photons can still work their way to us through the geometry of expanding space. And then there's the event horizon at roughly 16 to 17 billion light-years, which is not a statement about what's reached us yet, but about what can ever reach us in all of time going forward. Galaxies beyond the event horizon are sending us nothing and will send us nothing ever. And galaxies inside the event horizon but beyond the Hubble sphere are in a race. Their light is fighting expansion. But some of it wins. Some of it gets through. If you're only a little bit sleepy, you might find yourself wondering about those galaxies near the event horizon, the ones close to the line but on the inside of it. The ones whose light is currently in that tug of war, inching toward us against the flow. They're there. Their light is traveling. And if you could somehow intercept that light mid-journey and ask it whether it would make it all the way to Earth, the answer would depend on precisely where the galaxy sits relative to the event horizon today. Galaxies well inside it send us light that will arrive eventually. Galaxies right at the horizon send light that will take infinitely long to arrive, which is the same as never arriving. Galaxies just outside it send light that is right now still heading our direction, still crossing dark space, and will never close the distance. This is the loss that is already happening. Not in the future. Now. There is a further detail about how this loss actually looks. Not loss as in the galaxy simply disappears, but loss as in a slower, stranger kind of fading. And we'll come to it. But first, notice something that doesn't get said often enough. The event horizon is doing something the particle horizon is not. The particle horizon is growing, and the volume it encloses is getting slightly bigger. Every year, a little more of the cosmos becomes technically observable. But the event horizon, in terms of its relationship to the matter and galaxies distributed through space, is effectively contracting. Galaxies are steadily crossing from the reachable side to the unreachable side, and nothing crosses back. The set of galaxies we could ever receive a signal from, or ever visit, or ever influence in any way, is getting smaller. Not dramatically, not noticeably in a human lifetime, but continuously, always. There is no process that reverses this. You might wonder, and it's a good question if you're still awake enough for it, why the event horizon and the Hubble sphere are at different distances. Why is the event horizon bigger than the Hubble sphere? Shouldn't they be the same? The place where recession equals light speed, shouldn't that be exactly the place past which nothing can ever reach us? It would be in a universe that wasn't accelerating. If expansion were constant or decelerating, the Hubble sphere and the event horizon would sit at the same place. Any photon emitted from beyond the Hubble sphere in such a universe would indeed never reach us. But in an accelerating universe, there's a window of escape. The Hubble sphere itself moves outward over time as expansion changes, which allows some light emitted from beyond the current Hubble sphere to eventually find itself in a zone of slower recession and win its way to us. The event horizon accounts for this, baking in all future evolution of the expansion rate. It's the result of asking, given how expansion will change from now to forever, what's the true final boundary? The answer is the event horizon, a little larger than the Hubble sphere, but not by much. And because acceleration is happening, and because acceleration pulls the Hubble sphere out more slowly than it pulls galaxies away, the event horizon ends up being a finite limit. If expansion weren't accelerating, the event horizon would recede indefinitely and eventually include everything. If expansion weren't happening at all, there'd be no event horizon. You could reach anything given enough time. But we live in an accelerating universe, and that's the feature that closes the cage. The expansion is driven by dark energy, and we'll come to dark energy next, and to what it means that we've only known about it since 1998, and to the strangeness of its dominance. 68% of everything that exists, and we had no idea it was there until barely 25 years ago. There's a lot to say about dark energy, and it's the engine of everything in this story that carries the word loss in it. But for now, let's sit just a moment longer with the geometry, because there's something almost dreamlike about it if you let it settle. You're lying somewhere in the cosmos, on tiny rock, in a minor spiral arm of an ordinary galaxy, in a local neighborhood of a few dozen galaxies embedded in a larger structure of filaments and voids, and you are precisely at the center of your own observable universe. Not the center of the universe itself. The universe has no center, or perhaps every point is its center, depending on how you phrase it. But your observable universe, the sphere of everything that has had time to send you light, is centered exactly on you. Anyone, anywhere in the cosmos, has their own particle horizon centered on them, their own Hubble sphere, their own event horizon, which means there are galaxies that are inside our event horizon, reachable for us, that are outside the event horizon of some other observer. And there are galaxies in their reachable zone that we can never touch. Each observer is, in a way, marooned inside their own cosmic bubble of what's knowable and what's reachable, and the bubbles don't all overlap. And here's the final gentle image before we move on. You know how, if you stand on a cliff above the ocean and look out at the horizon, you can see roughly to a certain distance, depending on how high up you are. And beyond that distance, the curvature of the Earth drops everything out of view. The horizon is real. The ocean continues beyond it. There are ships out there past your sight. And yet, critically, the horizon is not a wall. It's a feature of your vantage point, your geometry, and your altitude. Move up higher and the horizon retreats. Descend and it closes in. The cosmic event horizon is something like this, but with a crucial, heartbreaking difference. At the ocean, if you climb higher, the horizon retreats and you see more. In the cosmos, there is no climbing higher. You cannot move the horizon. You are at the altitude you are at, and the expansion is doing what it does, and the horizon at 16 or 17 billion light years is, for our civilization, for all time, a final limit. Worse than that, it's a shrinking limit. Not in the sense that the number gets smaller quickly, but in the sense that the count of galaxies inside it is always falling, always, without reversal. A horizon that closes in and never opens back up. That's what we have. Now, it's worth pausing over something before we move on, something about where these galaxies actually are right now, compared to where they were when their light left them, because this is the kind of thing that can feel confusing in the night and then feels obvious in the morning, and it's worth having the clear picture. Take JDES GS-Z14-0. It's the most distant single galaxy we've confirmed, found by the James Webb Space Telescope in 2024. Its redshift is about 14.32, meaning the light from it has been stretched by a factor of roughly 15.3 since it was emitted. That light left the galaxy when the universe was only about 290 million years old, 290 million years after the beginning. The universe at that point was an infant. Stars had only just ignited for the first time. The first galaxies were barely taking shape, small and raw, and nothing like the grand spirals and ellipticals we see around us now. When that light left JD's GS Z14-0, the galaxy was, in terms of proper distance, the actual distance at that moment, a few billion light-years away. Close enough that the light could begin the journey, but in the 13.5 billion years since then, the expansion of space has carried that galaxy far, far out. Where is JD's GS Z14-0 now? Its current co-moving position, its current location in the cosmic grid, is something close to or perhaps beyond 30 billion light-years from us. We are seeing a snapshot of a place that has since retreated to distances no light could ever cross back from. Whatever JD's GS Z14-0 looks like today, if it still exists as a recognizable galaxy or has merged or evolved beyond recognition, we will never know. We have a photograph of its childhood. Its present is permanently beyond reach. And this is true not just for the most extreme cases. Every galaxy you see in the deep field images, those long exposure photographs where the Hubble Space Telescope or the James Webb gazed at a tiny patch of empty seeming sky and revealed thousands of smeared lights, each one a galaxy. Every single one of those is a historical record. You're seeing the past, in some cases the very ancient past. And the current state of those galaxies is not something we have access to, and in many cases never will. The light is a message in a bottle from a distant coast. By the time it arrives, the person who sent it has moved on, moved very, very far on. There's something worth saying here about the word look back. Astronomers use it, look back time, to describe the age of the light you're receiving. If you receive light from a galaxy with a look back time of 10 billion years, you're seeing that galaxy as it was 10 billion years ago. The light you're seeing tonight left on its journey when the universe was only 3.8 billion years old, when the first stars hadn't finished their brilliant short lives yet, when the cosmic web of filaments and voids was still thickening and taking shape. What you see in the telescope and what exists right now in that part of the universe are entirely different things. This is not a limitation we will ever overcome. It's not a technology gap. It's a physics fact. The speed of light is finite. The universe is large. The picture takes time to arrive. And in a cosmos where the distances are measured in billions of light years, the picture is always billions of years old when it gets here. So you have, if you hold all of this together, a finite observable universe that is the product of time and light speed and expansion, a particle horizon that is still barely slowly growing, a Hubble sphere beyond which recession exceeds the speed of light but through which some light can still escape. An event horizon that is the true limit, the final answer to what we can ever know, and which is contracting in terms of how many galaxies sit inside it, and a universe full of galaxies whose current state is not merely unknown to us but unknowable, because the light carrying their present-day information is either still in transit or never coming. Three edges, three very different stories, and only one of them, the event horizon, is the story of loss. Take a breath, if you like. There's no rush. The geometry can be a lot to hold at once, especially lying down with your eyes closed and the night settling around you. But you don't have to hold all of it perfectly. You don't have to get the exact numbers. What matters is the shape of the thing, that there is a distinction between what hasn't reached us yet and what will never reach us, and that the second category is growing, not shrinking. That every second, more of the universe moves permanently into the column labeled never. That this is not a future problem, but a present one. And there's still the question of what happens to the image of a galaxy as it crosses the event horizon. We said the galaxies don't blink out. So what do? This is where the strangeness gets beautiful. In a slow, melancholy kind of way. As a galaxy approaches the event horizon and finally crosses it, from our perspective, watching from here, its light doesn't stop arriving. Not immediately. The last photons emitted just before the crossing continue traveling toward us, even after the galaxy itself has gone beyond the line. But those photons are fighting the expansion, and they are losing. They are never gaining ground. And as they fail to gain ground, as the distance continues to grow, even though the photons are moving, those photons stretch. The wavelength of the light grows, the light reddens, it dims, and it continues reddening and dimming asymptotically forever. There's a perfect analogy in another context that you may have come across. In the physics of black holes, there is an edge called the event horizon. And the name, you'll notice, is the same word, for similar reasons. If you watch an object fall toward a black hole, what you see from a safe distance is the object approaching the horizon, slowing, reddening, dimming, and eventually freezing there. Stretched thinner and thinner, asymptotically still, never quite crossing in your view. It never winks out cleanly, it just fades infinitely slowly toward nothing, and the last light you receive from it is infinitely redshifted, infinitely dim, the memory of a thing that has technically not yet, from your vantage, fully crossed. A galaxy near our cosmic event horizon does something hauntingly similar. It doesn't vanish, it reddens, it fades, it appears to slow, the photons arriving more and more rarely as the expansion stretches them. And eventually its image would be so dim, so stretched to such long radio wavelengths, so nearly impossible to detect, that for any practical purpose it is gone from our sky. Even if, in some technical physical sense, a final infinitesimally faint ghost of a signal is still on its way. And the redshift of that signal climbs toward infinity as the galaxy recedes. At the event horizon, for an object right on the line, the redshift is infinite. The light is stretched to infinite wavelength, zero frequency, zero energy. There is no signal left. There is physically nothing arriving. So galaxies don't blink out like lights being switched off. They dim and redden and slow, and they are gone before they are gone, if that makes sense. They leave the census of the reachable universe in a long, quiet fade. And this is happening to galaxies right now. There are galaxies at intermediate redshifts, at around a redshift of 1.5 to 1.7, which cosmologists can connect to co-moving distances of around 5 gigaparsecs, around 16 to 17 billion light-years, that are right at the line or have just crossed it. Their light, emitted today, will never arrive. Their ancient light, emitted long ago, is already here, already in our data, already in our images. We can see them as they were. We cannot reach them as they are. And they are fading in the slowest, most gradual way out of the accessible universe. Abraham Loeb, a cosmologist at Harvard, wrote about this carefully in 2002. The paper was published in Physical Review D, and it was one of the first to lay out clearly not just the physics of the event horizon, but the practical, felt implication of it, that the set of galaxies we will ever be able to observe is finite, that we may already have received light from a large fraction of all the galaxies we will ever see, and that the universe available to future observers will be smaller, not larger. The reachable universe is contracting. Loeb's work is a quiet landmark in what you might call the cosmology of loss. And Loeb wasn't alone in this. In 2007, Lawrence Krauss and Robert Scherer published a paper in General Relativity and Gravitation, titled The Return of a Static Universe and the End of Cosmology. The title alone is enough to make you sit up a little. What Krauss and Scherer showed, building carefully on the physics of accelerating expansion, is that the far future of our universe is not just lonely, but epistemically devastating. Future astronomers, civilizations arising in the very distant future, will look up at the sky and find themselves apparently alone in a single galaxy surrounded by emptiness, with no evidence that any other galaxies ever existed, and no evidence of the Big Bang, and no evidence of the expansion of the universe. They will be unable, in principle, to discover the cosmological story we are still in the process of unraveling tonight. But that's the future. Let's stay here a little longer, in the present, with the three edges and the fading galaxies. Because there's one more thing to say about the size of what we don't know, the unobservable universe that lies beyond even our particle horizon, and it is considerably more staggering than anything we've covered so far. So let's talk about what is actually pushing all of this. What is the engine underneath the expansion, underneath the acceleration, underneath the event horizon that is quietly swallowing the reachable universe while you lie here in the dark? Because we've said the word expansion many times now, and we've said that expansion is accelerating, and that acceleration is the reason the event horizon exists at all. But we haven't yet sat with the thing responsible. And it deserves a moment. It deserves more than a moment, actually, because it is one of the strangest and most unsettling discoveries in the history of science. A discovery that almost didn't happen, made by people who were looking for something else entirely, and who found instead a result so deeply strange that their first instinct was that they must have made a mistake. The thing has a name. We call it dark energy. And dark energy, this is worth sitting with, comprises roughly 68% of everything in the universe. Not 68% of ordinary stuff, 68% of all the energy content, all the density, the entire budget of existence as best we can measure it. Ordinary matter, the atoms, the stars, the planets, the dust, the gas, everything you have ever touched or seen or thought about in your entire life, makes up about 5%. Dark matter, which we can detect only through its gravitational effects and cannot otherwise see or sample, accounts for roughly 27%. And the remaining 68% is this dark energy, this pressure or tension or property of space itself that we do not understand and cannot directly observe and cannot touch, which is nonetheless the dominant component of everything there is, and which is the reason the universe is expanding faster than it was yesterday. 68%, you are, in that sense, made of a tiny minority of what exists. The universe is mostly something we have no name for except a placeholder. Now, how do we know this? The discovery came in 1998, and it came not from a single flash of insight, but from two teams of astronomers who were, in a sense, racing each other, and who both found the same thing, and neither team was particularly happy about it. The first team was called the Supernova Cosmology Project. It was led by a physicist named Saul Perlmutter, working out of Lawrence Berkeley National Laboratory. The second team called themselves the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Both teams were doing the same basic thing. They were watching distant supernovae, specifically a type of stellar explosion called a Type Ia supernova. Type Ia supernovae are special. They are, in the vocabulary of astronomy, standard candles. A standard candle is something whose intrinsic brightness you know. You know exactly how bright it actually is, not just how bright it looks from here. And because you know how bright it actually is, you can measure how bright it looks and work backwards to find out how far away it must be. Type Ia supernovae all explode in a very similar way from a very similar kind of stellar remnant, releasing a very similar amount of energy, which means they all reach roughly the same peak brightness. They are, each of them, a lamp of a known wattage hung in the dark. If you see one and it looks dimmer than expected, you know it's farther away than expected. Both teams were using this technique to measure the history of cosmic expansion. The logic was straightforward. If you can measure how far away a supernova is, and you can measure its redshift, how much its light has been stretched by the expansion of space during its journey to us, then you can reconstruct how fast the universe was expanding when that supernova exploded. Do this for many supernovae at many different distances covering different epochs of cosmic history, and you map out the expansion over time. And back in 1998, both teams expected to find that the expansion was slowing down. This was the sensible prediction. The sensible prediction said gravity, the mutual attraction of all the matter in the universe for all the other matter, should be pulling things back together, should be putting the brakes on, gradually decelerating the outward rush. The question both teams were trying to answer was not whether the expansion was slowing, but by how much. They were trying to measure the deceleration. What they found was not deceleration. What they found was that the distant supernovae were dimmer than they should have been. Dimmer means farther. Farther than expected means the universe expanded more between then and now than it should have if it were simply coasting. It means the expansion, rather than slowing down, had been speeding up. Both teams thought they had made an error. They looked for it. They checked for dust in the intervening space that might dim the supernovae. They checked for subtle evolution in how Type Ia supernovae behaved at different epochs. They checked everything they could think of, and eventually, cautiously, both teams published, in 1998 and 1999, the same conclusion. The expansion of the universe is accelerating. The universe is not coasting, it is not decelerating, it is being pushed by something faster and faster, and whatever that something is, it is not matter, and it is not radiation, and it behaves in a way that is unlike anything we had ever built into our physics before. Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics in 2011 for this discovery, and the something that pushes, the agent behind the acceleration, is what we now call dark energy, formalized in cosmology as the LCDM model, the lambda cold dark matter model, where the Greek letter lambda, that little symbol, represents the cosmological constant. Einstein had actually introduced the cosmological constant decades earlier as a fudge factor to keep the universe from collapsing in his equations, and he later called it his greatest blunder when Hubble's observations showed the universe was expanding anyway. But Einstein's blunder turned out to be right. The cosmological constant, or something that behaves like it, appears to be real. Lambda, that little symbol on a whiteboard, turns out to be the dominant feature of the universe. And here is what that means physically as best we understand it. Empty space, vacuum, has an energy. Not zero energy, some small positive energy density built into the fabric of space itself. And as the universe expands, as space grows, there is simply more of that space and more of that energy, which means the accelerating push grows as the universe expands, which means the expansion accelerates faster, which means more space, which means more dark energy, which means more push. It is a self-reinforcing process. The universe is not merely expanding, it is running away. Which brings us back to the event horizon, because the event horizon, that boundary at roughly 16 billion light-years in co-moving distance, the line beyond which no signal sent today will ever reach us, exists precisely because of this. It exists because the acceleration is strong enough that light from beyond that boundary, light trying to cross the gap toward us, is trying to swim upstream in a river that is flowing outward faster and faster. The light moves at the speed of light. The space it is traveling through expands, and for sources beyond the event horizon, the space between them and us is expanding fast enough and accelerating fast enough that the light loses ground. It cannot make up the distance it needs to make. It swims and never arrives. Abraham Loeb, working at Harvard, calculated in 2002 the precise implications of this for our cosmic future, publishing in Physical Review D. And what he found was this: there is a boundary, the event horizon, at around 16 billion light-years in co-moving coordinates. And anything emitting light today from beyond that boundary cannot send us that light. The light from today, from objects at that distance and beyond, will never reach us. Now, this horizon is not fixed in the way you might picture a wall. It moves, or more precisely, it contracts relative to the matter in the universe. Galaxies don't move into the forbidden zone. They are, remember, mostly staying at roughly fixed, co-moving positions. It's space itself that expands between them. But because space is expanding faster and faster, and because the event horizon is set by the physics of how fast that expansion is happening, the set of galaxies that fall outside the event horizon, the set of galaxies from which no future signal can reach us, is growing. Galaxies are crossing the event horizon in the sense that the expanding space between them and us is carrying them from the reachable side to the unreachable side, not moving through space, being carried by space. Loeb's calculations and later work by Berta Margalef-Bentebol and colleagues on the evolution of cosmological horizons, published in 2012 and 2013, make this concrete. The event horizon, in comoving distance, is not growing. It is approaching a finite limit and effectively contracting relative to the co-moving positions of matter, which means more and more galaxies are on the wrong side of it, which means the number of galaxies from which we can still receive a signal today is falling, which means the reachable universe is shrinking. This is happening right now, not in a billion years, not in some future epoch we will never see. Right now, as you breathe, as the Earth turns, as the photons of distant galaxies begin their journeys across the dark, some of those photons will cross from a galaxy that is on the reachable side of the event horizon to a galaxy that is on the unreachable side. And that transition, that crossing, means those photons will never arrive. The light leaves, and it never gets here. How quickly does this happen? This is where honesty matters, so let me be careful. The figure you sometimes hear, that tens of thousands of stars worth of light are lost to us every second, tens of thousands of stars crossing beyond the event horizon every second, is not a measured constant. No one has counted them one by one. What it is, instead, is an order of magnitude estimate, a number derived by taking what we know about the rate at which the event horizon is contracting relative to co-moving matter, combining that with estimates of how many galaxies lie near the horizon and how many stars those galaxies contain, and working out approximately how many stars per unit of time find themselves newly beyond the line we can never cross. The calculation is defensible. The underlying physics is solid, but treat the number as an illustration, not a census. Think of it not as a precise measurement, but as a feel for the scale of what is happening, because the scale, even approximately, is the thing worth sitting with, not tens, not thousands, tens of thousands, every second. And the reason this matters is that it underlines something Loeb's work made very clear. This is not an event that is coming, it is an event that is ongoing. The loss is present tense. The universe we can ever touch has been smaller this second than it was the second before, and smaller yesterday than it was the day before that, and has been this way since dark energy began to dominate the expansion, which happened roughly 5 to 6 billion years ago. For longer than the Earth has existed, the reachable universe has been shrinking. You are not watching a wound being inflicted. You are observing a wound that is already old. But here's a thing I want to linger with for a moment, because it's one of the stranger details in all of this, and it's easy to pass over too quickly. When we say that a galaxy crosses the event horizon, what does that actually look like? What happens to the light it sends afterward? What happens to the last light it sent before? It doesn't blink out, it doesn't disappear, it doesn't simply vanish from the sky one day as though someone switched off a lamp. What happens is much more gradual, much stranger, and in a way much more haunting. Think about what happens to light as it crosses a very large distance in an expanding universe. The light is stretched. The wavelength of the light, the distance between one crest of the electromagnetic wave and the next, grows longer as the space it is traveling through expands. Short wavelengths are blue. Long wavelengths are red. Very long wavelengths are infrared, invisible to the eye. Longer still, and the wavelength passes out of infrared into microwave, into radio. This stretching is what we call redshift, and we describe it with the symbol Z, where Z equals 0 means no stretching at all, and Z equals 1 means the wavelength has doubled, and Z equals 1,100 means the wavelength has stretched by a factor of 1,100. That's the cosmic microwave background, the oldest light we can see. Now, as a galaxy approaches and then crosses the event horizon, the light it sends toward us is emitted at higher and higher redshift. The light from the galaxy slows in a sense. The frequency of photons arriving at our location decreases because the space they are crossing is expanding faster, because it takes longer for each successive photon to make the journey. And as redshift increases, brightness falls. The galaxy dims and reddens as the light that reaches us gets stretched further and further toward the red end of the spectrum and then past the visible spectrum into the infrared and beyond. There is a point at which a galaxy's light has been redshifted so far, stretched so long, that it falls below any detector we could ever build, not because of a technological limitation we might someday overcome, but because the quantum of energy carried by each photon has been diluted to almost nothing. A photon stretched to an infinitely long wavelength carries essentially zero energy. And as a galaxy asymptotically approaches and crosses the event horizon, the photons it sends toward us are asymptotically approaching infinite wavelength and zero energy. The galaxy does not blink out. It fades and reddens and slows to a red whisper, and eventually falls into silence so complete that it might as well never have existed. Loeb noted that this is strikingly similar to something you might have heard about in a completely different context. What happens, as seen by a distant observer, when an object falls into a black hole? An object falling toward a black hole, from the perspective of someone watching from outside, never quite reaches the event horizon. The light from that object is stretched by the intense gravitational field, redshifted, dimmed. The object appears to slow and redden and freeze at the horizon, asymptotically approaching but never quite arriving. It is not that the object disappears, it is that its image stretches toward infinite redness and infinite faintness, and the last light you receive from it is the last message it was able to send before the horizon closed around it, held in stasis at the boundary forever. This is the same physics, a different geometry, a different scale. Instead of the immense gravity of a black hole, it is the accelerating expansion of the universe itself. But the mathematical structure is nearly the same. A galaxy crossing our cosmic event horizon sends us light that is redshifted to infinity. Its last photons are stretched to infinite wavelength. It freezes at the horizon, fading, its image an afterimage of a world we can no longer reach. And then, silence. The universe, in a sense, is becoming a kind of inside-out black hole. We are on the inside of an event horizon that is closing around us, not in the sense that we are trapped or in danger, but in the sense that the geometry of our universe, a universe with a cosmological constant, a universe dominated by dark energy, approaches what physicists call de Sitter space. The physicists Stephen Hawking and Gary Gibbons showed in 1977 that de Sitter space has its own event horizon, and that this horizon has its own temperature, the Gibbons-Hawking temperature, and its own entropy, in mathematical analogy with a black hole's horizon. We live, or will live, in a universe that is in this deep structural sense the inside of a very large, very cold, very slowly radiating cosmic horizon. You don't need to follow every step of that mathematics to feel the shape of it. The point is this: the horizon is real, the loss is real, and the mechanism behind the loss, dark energy, pressing outward, pressing the far universe away from us faster than light can cross, has a shape that is not arbitrary, not a quirk of initial conditions, but a fundamental feature of the kind of universe we inhabit. Now, let me be precise about where the event horizon sits, because this matters enormously for understanding the scale of what we're losing. The event horizon currently lies at approximately 16 to 17 billion light-years in co-moving distance. The observable universe, the particle horizon, the boundary of everything we have ever or could ever see since the Big Bang, is at about 46.5 billion light-years in co-moving distance. The event horizon is much closer, and beyond the event horizon, in the enormous volume of space between roughly 16 billion light-years and 46.5 billion light-years, there are vast numbers of galaxies. Galaxies we have received ancient light from, galaxies some of whose light still lives in our observable universe as a historical record, but galaxies from which any signal sent now will never reach us. We are watching their past, their present, and their future are permanently out of reach. And that's already remarkable, but the next part is where it gets quieter and stranger and more final. Think about what it means to try to do astronomy in the far future. Not next century, not next millennium, but in a time so distant it is difficult to find an analogy, a time in the range that Lawrence Krauss and Robert Scherer calculated in their 2007 paper, roughly 100 billion to 1 trillion years from now. In that time, the universe's expansion will have been running for 100 times longer than it has run so far, or 1,000 times longer. Dark energy will have had all that time to push and push and push. The event horizon will have long since swept past the last visible galaxies. Every galaxy outside our local group, the gravitationally bound cluster of which the Milky Way and Andromeda and roughly 80 smaller satellite galaxies are members, will have been carried beyond the horizon, redshifted to silence, their last fading photons long since stretched into wavelengths so long they carry no information. The sky will be empty. Not metaphorically empty, literally, observably, measurably empty in every direction of everything except the single merged galaxy that will by then have formed from our own local group. Krauss and Scherer showed something deeply troubling about this. They showed that the cosmic microwave background, the faint glow of the Big Bang itself, the light that has been traveling toward us since 380,000 years after the universe began, the fundamental evidence for what happened at the start, will, in that distant epoch, have been redshifted so far that it will have dropped below the plasma frequency of the interstellar medium. What this means is that the interstellar medium, the diffuse gas that fills the space between stars inside the galaxy, will effectively be opaque to the CMB. At those wavelengths, the CMB will be undetectable. The evidence for the Big Bang will be gone. Not lost in the sense of being somewhere we can't reach. Lost in the sense of having been stretched into a form that carries no recoverable information. And at the same time, all the other galaxies will be gone. There will be no Hubble law redshifts to measure, because there will be nothing to measure them on. There will be no distant supernovae to track, because there will be no accessible distance ladder stretching beyond the single merged galaxy in the sky. There will be no evidence of expansion, because from a single island galaxy in an empty void, the universe will appear static. It will appear eternal. It will appear to every observation a future civilization could make to have always been this way, one galaxy, one island, surrounded by nothing forever. And here is the thing Krauss and Scherer found most poignant, most disturbing. Future astronomers, intelligent beings perhaps arising in that distant epoch, curious about the same questions we are curious about tonight, will not be able to discover what we have discovered. They will look up at their sky, they will map the stars of their galaxy, they will develop their physics, and they will have every reason to conclude, based on all available evidence, that the universe is static, eternal, and alone. They will not have access to the evidence that would tell them otherwise, because the evidence will have been written on light that was long ago redshifted into silence. They will be wrong, but they will have no way of knowing they are wrong. And we know this. We can see from our position in time, this specific, narrow, cosmically brief window of time, the entire story. We can see the evidence of the Big Bang. We can measure the CMB. We can see thousands of billions of galaxies spread in every direction. We can measure the expansion. We can work out the fate. We can know that the universe was once so different from what it is now that it was essentially a single fireball, and we can trace the story from there to here, and from here to a final silence. Future beings in that distant epoch cannot do this. They will be born into the silence. They will have no memory of the full sky because there will be no record of it, no starlight from distant galaxies, no CMB signal to decode, no expansion to measure. The story will be gone. But before we follow that thread all the way out, let me stay here a moment longer with the event horizon and with a number. We said that even at the speed of light, we could only ever reach about 3% of the galaxies we can currently observe in the observable universe. This figure, worked out by Abraham Loeb and developed further by others, including Toby Ord in 2021, comes from comparing the volume of space within the cosmic event horizon, within that roughly 16 to 17 billion light-year co-moving boundary, to the total volume of the observable universe, which extends to 46.5 billion light-years. The event horizon is not a small fraction of the observable universe. It is enormous by any human scale, but it is substantially smaller than the observable sphere, and the number of galaxies scales roughly with volume, so the fraction of galaxies we could reach, galaxies we could send a signal to, galaxies we could travel to even in a hypothetical ship capable of reaching the speed of light, is somewhere in the neighborhood of 3% of what we can see. 3%. This means that 97% of the galaxies we observe in our night sky, roughly speaking, are already beyond us. Not beyond us in the sense that we haven't gotten there yet. Beyond us in the sense that we will never get there, not even if we start now, not even if we could somehow travel at the speed of light, not even given infinite time. The light from those galaxies is visible. Their history is recorded in the light that has already reached us. But their present and their future and any possible contact between us and them is gone. There is a specific redshift that marks this line. Galaxies we observe at a redshift of roughly z equals 1.5 to 1.7. Galaxies whose light was emitted when the universe was about 4 to 5 billion years old are already today beyond our event horizon. The light we receive from them is old light, ancient light, emitted long ago when those galaxies were on the right side of the line. Since then, the acceleration has pushed them across. We are watching their past. We cannot touch their present. And this is the image I want to stay with for a moment, because it is one of the stranger things in all of cosmology. You look at the night sky, not with a telescope, just with your eyes on a clear night, wherever you are. You see stars, mostly in our own galaxy, but embedded in the deeper dark, those faint smudges that a telescope would resolve into galaxies, those ghostly islands. Some of what you are looking at is light from a time when those galaxies were reachable. Some of it is the last light we will ever receive from them, or nearly so. Some of it is from galaxies that are already on the far side of the event horizon, already past the line, already lost in the physical sense that no signal from now on can bridge the gap. And you don't know just by looking which is which. The sky does not annotate itself. It does not label the lost from the still reachable. It just shines, and it does not tell you that some of what you are seeing is a world you have already permanently missed. The light arrives, the galaxies recede, the event horizon contracts, the loss accumulates, and somewhere in the enormous volume of space between the event horizon and the edge of the observable universe, in the vast region that is visible but unreachable, there are galaxies. Many, many galaxies. Estimates of the total number of galaxies in the observable universe, working from data like the Hubble Deep Field, extrapolated across the full sky, come in at roughly 2 trillion from work by Christopher Consolis and colleagues published in 2016. More recent analysis from the New Horizons spacecraft measuring the cosmic optical background by Todd Lauer and colleagues published in 2022 suggests the number might be lower, closer to a few hundred billion. The exact count is uncertain, but even at the lower end, even if the number is a few hundred billion rather than 2 trillion, the vast majority of those galaxies are outside our event horizon, and the ones that are inside it, the ones still technically reachable, number in the tens of billions at most. 3% of hundreds of billions is still an enormous number, but it is 3%. The rest are already gone. And they are not gone in the trivial sense that they are far away. They are gone in the deep sense that no amount of time, no future technology, no civilization of any imaginable sophistication could ever bridge the gap. The physics closes it. The expansion of space, dark energy, that 68% of everything pressing outward faster and faster makes the distance increase faster than any possible signal can travel. It is not an engineering problem. It is a feature of the universe we live in. Dark energy does this. That 68%, that quiet, dominant feature of everything, that almost nothing, that nevertheless outweighs all the matter in the cosmos, is the reason the loss is real and permanent rather than merely distant and difficult. And we don't entirely know what dark energy is. We know what it does. We know it accelerates the expansion. We know it behaves, as far as we have been able to measure, like a constant energy density in empty space, and the cosmological constant, Einstein's lambda, the term he introduced and abandoned, and which turned out to be real. We know it accounts for 68% of the universe's energy budget as measured by the Planck satellite. We know that the LCDM model, with dark matter and dark energy and cold dark matter and the cosmological constant, fits the observations we have better than any competing framework. But we do not know what lambda actually is. We do not know why empty space has the energy density it has. We have theoretical calculations from quantum field theory that predict a vacuum energy density, but those predictions are off by a factor of something like 10 to the power of 60 or 10 to the power of 120, depending on how you count. The most spectacular mismatch between theory and observation in the history of physics. We do not know if dark energy is truly constant or whether it changes over time. We measure it to be very close to constant, but very close is not the same as exactly. And in 2024, a large collaboration of astronomers and physicists using an instrument called the Dark Energy Spectroscopic Instrument, DESI, a remarkable array of 5,000 robotic fiber optic positioners mounted on a telescope at Kitt Peak National Observatory in Arizona, published preliminary results from their first data release that hinted, tentatively, that dark energy might not be perfectly constant. The DESI results measured the clustering of galaxies and quasars across a vast range of cosmic distances, and the statistical patterns they found suggested a possible variation in the dark energy equation of state over time, a hint that the energy density of the vacuum might be evolving. The results are preliminary, they are actively debated. The hint might be a statistical fluctuation that further data will wash away, or it might be a genuine signal. If it is a genuine signal, it matters enormously. Not because a slowly changing dark energy is necessarily catastrophic. A weakening dark energy might even slow the loss of the reachable universe slightly if it reduced the acceleration. But because it would mean the cosmological constant is not a constant at all, that the physics underlying the acceleration is richer and stranger than we thought, and that the fate of the universe, the final shape of what will be lost and when, is not yet fully written. This is one of the most important open questions in all of science, and the 2024 DESI results are, cautiously, a possible first look at an answer, or at least at a deeper version of the question. But what we know now, what the 1998 supernovae discoveries of Perlmutter and Schmidt and Rees told us, what the Planck satellite confirmed and refined, is that the acceleration is real, that dark energy is real, and that the event horizon is real. The engine is running, the horizon is contracting relative to the matter of the cosmos, and galaxies, one by one, continuously, are crossing it. Each one carries its stars with it into the unreachable. The light those galaxies already sent toward us will keep arriving for millions and billions of years. Ancient light, historical light, the long echo of a past before the loss was complete. But the galaxies themselves, in their present moment, are already on the far side of a line we cannot cross. We are watching the past of the unreachable. We are reading a letter from someone who has already moved permanently to somewhere we will never find. And as the light of each galaxy is stretched toward the infrared and beyond, as the redshift climbs toward infinity and the energy of each photon approaches zero, the galaxy does not vanish from the sky all at once. It dims, it reddens, it slows. It is like watching a fire die. The embers lose their orange and go to dull red, and then to a heat you can feel but not see, and then to nothing. The last photons from galaxies crossing the event horizon arrive, stretched to wavelengths no detector could capture, carrying energies too small to trigger a single atom. And then they are gone, and the galaxy that sent them is permanently, irretrievably silent, frozen at the horizon. Not destroyed, not gone in the sense of annihilated. Still existing in some region of space we will never reach, still full of stars and gas and whatever life has found a foothold there, but causally disconnected from us, permanently and irrevocably, by a boundary made not of matter, but of geometry. The geometry of a universe running away from itself under the pressure of its own dark energy. It is, in its way, the loneliest fact in physics, and we discovered it only in 1998. For all of human history before that, we had no idea the universe was accelerating. We assumed that expansion was decelerating, that gravity was pulling things back, that the future would be gentler than the evidence suggests. Two teams of astronomers looking at the dimness of distant supernovae changed that. A Nobel Prize in 2011 marked the moment when the scientific community formally accepted that this strange and unsettling thing was true. So here we are, on the near side of the event horizon, watching the galaxies freeze and fade, surrounded by the vast and mostly unreachable, in possession of a window of time, cosmically brief, cosmically irreplaceable, in which the evidence of the full universe is still visible, and the story of where all of this came from is still written in the sky in light we can actually read. And beyond the event horizon, beyond the observable universe, beyond the particle horizon at 46.5 billion light-years, there is more, much more. The question of how much more and how vast the universe is beyond what we will ever see is where we are going next. And the answer is staggering enough that it will take a moment to absorb, because the observable universe, large as it is, large as it must now seem to you, nearly 100 billion light-years across, containing hundreds of billions or perhaps 2 trillion galaxies, may be to the full universe what a single droplet of water is to the ocean, or less than that, much less. So let's sit with that for a moment, because what comes next requires a certain quietness of mind to really take in. We have been talking all this time about the observable universe, the sphere of space from which light has had time to reach us, roughly 46.5 billion light-years in every direction, the particle horizon, the boundary of what we can see. We have been talking about the event horizon inside that, the closer and more consequential edge at around 16 billion light-years, the boundary of what we can ever reach or ever receive signals from. Those are large numbers, almost uselessly large by everyday standards, and yet Vardanyan, Trotter, and Silk, astronomers who published their analysis in 2011, worked through what the best available measurements of the universe's geometry could tell us about the universe's true size, the total universe, not just the observable patch. And what they found was this: the total universe, the full extent of space, including all the regions we will never see, must be at least 250 times larger in volume than the observable universe. At minimum, a lower bound. Not the likely size, only the minimum. 250 times larger, let that sit for a second. Take your observable universe with its hundreds of billions of galaxies, its uncountable trillions of stars, its unimaginable depths of space, and understand that this, all of this, may represent less than half of 1% of everything that exists. Less than a single droplet in an ocean that stretches beyond any horizon you could ever approach. And the reason we can say at minimum and not give you an upper bound is that the upper bound may not exist. The universe, based on measurements made by the Planck satellite of the cosmic microwave background, appears to be flat, geometrically flat, to within about 0.4%. And what flatness means in cosmology is that the geometry of space is not curving back on itself the way the surface of a sphere does. It extends outward indefinitely, without looping, without returning to its starting point. A flat universe is mathematically a universe that could be infinite. Infinite. Actual infinite. Not very large, not effectively infinite. Infinite. As in no end, no edge, no outside. Now, this is a place where the mind does something strange. It reaches for the edge and finds nothing to grab. And most people, encountering this for the first time, feel a mild vertigo. That is the correct response. You are not missing something. The strangeness is the truth. But here's where it gets interesting. Even if the universe is infinite, even if space extends without end in every direction, filled with galaxies and stars and perhaps other stories we will never hear, we would still be confined forever to our tiny observable patch. The infinity would be real and we would never touch it. The universe would be infinitely larger than our access to it, and that excess, that unimaginable surplus, would be functionally invisible. We would see our sphere, our 46.5 billion light-year bubble, and beyond that, nothing. Not because there is nothing, but because there is no light that has had time to bring us news of it. And this is the thing about inflation that makes it more than just a curiosity. Cosmic inflation, the idea proposed by Alan Guth in 1981, describes a process that happened in the very first sliver of time after the Big Bang, when the universe expanded not gradually but explosively, exponentially, in an interval so brief it is essentially unrepresentable in everyday terms, something on the order of 10 to the negative 32 seconds. The universe inflated by a factor of at least 10 to the 26th power. That is, it expanded by more than 1 trillion times in a fraction of an instant. What that means in practice is that the region of the universe we now inhabit, the entire observable universe, everything within 46.5 billion light-years in every direction, began as a single, extraordinarily tiny patch, a patch that was in causal contact with itself, that was able to smooth itself out and reach nearly uniform temperature before the inflation began. And then that patch was inflated to astronomical scales, and the regions around it, regions that were also in causal contact with their own neighbors, were also inflated, and so on and outward without bound, if the universe is indeed infinite. This is why the universe is so much larger than the observable patch. It is why the flatness is so precise. It is why the cosmic microwave background looks so uniform in every direction, because everything we can see came from a single tiny region that had time to equilibrate before the inflation stretched it vast. And it means that the 250 lower bound Vardanyan, Trotter, and Silk computed is almost certainly a dramatic underestimate of the true scale. Inflation models suggest the universe could be so much larger than the observable patch that the phrase "much larger" is itself an absurd understatement. The observable universe in some of these models would be to the full universe what a single proton is to the planet you are sleeping on, not a metaphor for emphasis. An honest comparison of scales, there is no light from those regions, there is no news, there is no way of ever knowing, and yet, if the physics is consistent, as if the laws that govern our patch govern the whole, then out there, unreachable, undetectable, untouchable, the same stars are burning, the same dark energy is pushing, the same drama is playing out in every direction forever. That is either the most comforting thought imaginable or the most isolating one. Perhaps it is both, which is why it tends to arrive quietly rather than loudly, settling in slowly like a weather change rather than landing all at once. So, the unobservable universe is vast beyond any reckoning, and the observable universe, already nearly 100 billion light-years across, is a tiny window onto it. A window that is, in comoving terms, bounded. A window that has been slowly revealing more as more ancient light trickles in, but which is approaching a limit, an asymptote, beyond which no new information will ever come. And within our observable universe, within the 46.5 billion light-years, we have the event horizon, that inner edge at around 16 billion light-years, beyond which galaxies are leaving and will never return to our reach. And most of the galaxies we can see are already beyond that inner edge. Most of what we can observe, we cannot touch, cannot reach, cannot ever signal to. The observable universe and the reachable universe are not the same thing, and they have not been the same thing for some time now. But here is the thing. There is a corner of the observable universe that is different. A small, gravitationally bound cluster of galaxies in which the rules are different. A place where the expansion of space, the dark energy, the retreating tide, none of it applies. A place that is, in a cosmic sense, home. We call it the local group. The local group is a collection of roughly 80 galaxies, most of them small dwarf galaxies, satellites of the larger ones, held together by their mutual gravity, the Milky Way, Andromeda, the Triangulum galaxy, a smaller spiral, dozens of dwarfs. They are gravitationally bound, and when something is gravitationally bound, it is decoupled from the cosmic expansion. The space between us and Andromeda is not expanding. It is not being stretched by dark energy. The gravitational attraction between us is strong enough to overcome the expansion on these local scales, and so the local group is not flying apart. It is, in fact, moving together. And here is one of the few places in the universe where we observe something that, against all intuitions built up by everything else in this video, is moving toward us rather than away. Andromeda, M31, is blue-shifted. Its light, rather than being stretched toward red by recession, is compressed toward blue by approach. It is heading in our direction at roughly 110 kilometers per second, measured precisely with Hubble Space Telescope proper motion data by Roland van der Marel and his team in 2012. 110 kilometers per second sounds fast. In everyday terms, it is. In cosmic terms, it is a gentle drift, and the distance involved, roughly 2.5 million light-years, means that this gentle drift will take time to close, approximately 4.5 billion years, give or take. In about 4.5 billion years, Andromeda will arrive. And what happens when two large spiral galaxies arrive at each other is not a collision in the way you might picture it, not a crash, not a sudden smashing of stars into stars, because the stars within each galaxy are so widely spaced that most of them will simply pass through one another's galaxy like two swarms of bees merging. But the gravitational dynamics will reshape both galaxies utterly. They will swirl and distort and throw streamers of stars into intergalactic space, and eventually, over billions of years, they will settle into a single merged object. A large elliptical galaxy, no longer spiral, no longer structured the way either of its parents were. Astronomers have taken to calling this future merged galaxy Milkomeda, a portmanteau, our galaxy and Andromeda fused into one. And this is where the story becomes simultaneously large and small, because Milkomeda will not be a tragedy. It will be a survival. The local group, whatever it is called, whatever shape it takes, will persist. It will be gravitationally bound. It will be in a universe that is otherwise flying apart, a held thing. Because everything else, every other galaxy beyond the local group, will be gone. Not suddenly, not all at once, but inexorably, on time scales that dwarf the current age of the universe. Let's move forward in time now, not a little forward. Let's go all the way, it's not to 4.5 billion years, which is merely when Andromeda arrives, but to something like 100 billion years from now, or 500 billion, or 1 trillion. This is where Lawrence Krauss and Robert Scherer take over the story. Krauss and Scherer published their analysis in 2007 in the journal General Relativity and Gravitation, and what they described is one of the most quietly devastating things in all of cosmology. They asked, what will future astronomers be able to discover about the universe? Not our near future, not astronomers a few centuries ahead. Future astronomers in the far, far future, perhaps 100 billion or 1 trillion years from now, living in whatever our galaxy has become. What will the sky look like to them? What evidence will be available to reconstruct the history of the cosmos? And the answer is almost none. Here is why. Right now, we live in a cosmologically unique moment. The universe is 13.8 billion years old, which is young enough that the light from the Big Bang is still observable. The cosmic microwave background, the afterglow of the universe's first moment of transparency, still fills the sky at a temperature of just under 3 degrees Kelvin, and it tells us, unmistakably, that the universe began in a hot, dense state. The galaxies beyond our local group are still close enough, relative to what they will become, that we can detect them, measure their redshifts, trace the expansion, and reconstruct the history of how the universe grew from that hot beginning to the vast and cooling structure it is now. The evidence is all still there, like letters, still legible on an old page. But time and dark energy are eating the page. As the universe continues to expand, and as that expansion continues to accelerate, the galaxies beyond our local group will drift further and further away. Their light will redshift further and further toward the red, and then toward the infrared, and then toward the microwave, and then toward wavelengths so long that they carry essentially no energy. There is a threshold, a wavelength so long that the photons literally cannot propagate through the thin plasma of the intergalactic medium because the medium itself absorbs them. The photons fall below what is called the plasma frequency of the interstellar medium. Below this frequency, the universe is opaque in a new way, not because of the hot plasma of the early universe, but because even the thin medium of the late universe blocks photons that are too feeble, too long in wavelength, too red. Krauss and Scherer calculated that the cosmic microwave background, the foundational evidence for the Big Bang, will be redshifted past this plasma frequency on a time scale of roughly 100 billion to a trillion years. At that point, it simply cannot be detected by any instrument imaginable, because there is no longer any instrument in any imaginable frequency band that can receive the signal. The CMB will be gone, not because it stops existing, but because the universe will have redshifted it into indetectability. And simultaneously, all the galaxies beyond our local group, already retreating, already sending light that is increasingly redshifted, will have crossed the event horizon entirely. No light from them will be arriving. The sky beyond Milkomeda will be dark, not dim. Dark, empty, a void. So the astronomer of a trillion years from now, sitting somewhere in Milkomeda, will look out at the universe and see what? One galaxy, just one, surrounded by emptiness, no CMB, no distant galaxies, no Hubble flow to measure, no cosmic expansion detectable, no evidence anywhere that the universe ever contained anything other than this one island of light in a sea of perfect darkness. And they will, using the best physics they have, reach a conclusion, a reasonable conclusion, based on the evidence available to them. They will conclude that the universe is static, that it has always been this way, that there was no Big Bang, no expanding cosmos, no grand history of growth and structure. And they will conclude essentially that the universe is eternal and changeless, a single galaxy in an infinite void, and they will have no way of knowing, no way that can even in principle be constructed, that this is wrong. Krauss and Scherer were careful to say that this is not merely sad, it is, in fact, a warning about the contingency of knowledge. The knowledge we have accumulated about the universe's history and structure was only possible because we live in a particular window of time. A brief window by cosmic standards, a window that is already, if slowly, beginning to close. The CMB is still detectable now, but it is weaker than it was. The galaxies are still visible now, but they are dimmer than they were. The expansion is still measurable now, but the best tools we have for measuring it, the distant supernova, the baryon acoustic oscillations, rely on objects that are, from the perspective of the event horizon physics, already close to or beyond the edge. We are, right now, close to the peak of our cosmic observational capability. Not quite at the peak. There may still be some slight improvements as more of the observable universe's light continues to trickle in, but we are close. And we are certainly not far from the point at which the observable universe begins to shrink faster than new information arrives. Future astronomers in the near future, 1 billion years from now, 10 billion years from now, will likely have better technology than we do, but they will have worse data because the universe will have handed them a poorer situation to observe, and astronomers 10 trillion years from now will have the best conceivable physics and the worst conceivable cosmological evidence. We are the lucky ones. Now, let's take a breath and come back to the question of what happens at the very end, because we have talked about the local group surviving and about Milkomeda forming and about the eventual isolation of this one merged galaxy in the void. But what happens to the universe beyond that isolation? This is where the story divides and where honesty requires us to say that we do not yet know which branch is the true one. The first possibility is the one that follows from what we currently believe about dark energy, that it is a cosmological constant, a fixed energy density built into the vacuum of space itself. If dark energy is constant, the universe continues to expand forever, and the expansion continues to accelerate forever, but the expansion rate remains bounded. Galaxies continue to separate, but within Milkomeda, the stars burn on. The local group, Milkomeda, will continue forming stars for many trillions of years. The last stars to burn will be the red dwarfs, the smallest and most frugal of stellar types, which can persist for up to roughly 100 trillion years before exhausting their hydrogen fuel. That is 10 to the power of 14 years compared to the universe's current age of roughly 10 to the power of 10 years. The universe we know is early middle-aged. The era of stars is a long way from over. But eventually the gas runs out. The last red dwarf cools and fades. Stars stop forming because there is no more raw material. The universe enters what cosmologists Fred Adams and Gregory Laughlin in their 1997 paper called the degenerate era. An age of white dwarfs, neutron stars and black holes, relics of earlier stellar generations, cooling and dimming over immense timescales as even those last embers fade. And much further on, the black holes evaporate via Hawking radiation. Takes an extraordinarily slow process, and the universe approaches something close to maximum entropy, maximum disorder, minimum useful energy, heat death, the big freeze. Not a sudden ending, but an asymptotic approach to a state of utter stillness in which nothing more can happen, because there is no longer any energy gradient available to drive any process. That is one ending. Gradual, slow. The universe winding down like a clock that has been ticking for an eternity, finally coming to rest. The other possibility is sharper, more violent. And it depends on dark energy doing something other than remaining constant. We know that dark energy comprises roughly 68% of the total energy density of the universe, with dark matter at roughly 27% and ordinary matter, stars, gas, planets, at roughly 5%. These are the Planck 2018 numbers, and they are the best measurements we have of the fundamental composition of everything. But what we do not know is whether dark energy's density is truly constant or whether it evolves over time, whether it might be growing. Robert Caldwell, Mark Kamionkowski, and Nevin Weinberg described in a 2003 paper what happens if dark energy has what is called a phantom energy character. If the dark energy density actually increases as the universe expands rather than staying fixed. The implications are extreme. If dark energy strengthens over time, then the acceleration of the universe does not merely continue, it intensifies, and eventually on some finite timescale, the acceleration becomes strong enough to overcome not just gravity between galaxy clusters, not just gravity within galaxies, but gravity within solar systems, then within planetary systems, then within planets and stars, then within molecules, then within atoms. In the Big Rip scenario, the force of accelerating expansion eventually tears apart every structure in the universe on every scale down to the subatomic. Galaxies shred first, then solar systems, then planets, then, in the final seconds, atoms themselves. The dark energy ripping apart the nuclear forces that bind protons and electrons would cease to exist as coherent structures. The universe ends not in a fade, but in a tearing apart of everything at once, simultaneously, everywhere. The timescale for the Big Rip, if phantom energy is the correct description of dark energy, depends on exactly how quickly the dark energy density grows. But estimates put it at somewhere between tens of billions to hundreds of billions of years from now. So which is it, Big Freeze or Big Rip? We do not know, and this is where something very recent and very important enters the story. In 2024, the Dark Energy Spectroscopic Instrument, DESI, an extraordinary facility in Arizona that has been mapping the positions of tens of millions of galaxies to trace the history of the universe's expansion, released its first major data results, the DR1 baryon acoustic oscillation findings. And what those results hinted at, tentatively, carefully, with all the appropriate scientific caveats about early data and the need for confirmation, was that dark energy might not be a perfect constant after all. The data, analyzed by the DESI collaboration, showed hints of what they described as evolving dark energy. Not phantom energy, not the Big Rip variety, but a dark energy whose strength may be changing over time, perhaps weakening slightly, perhaps doing something more complicated. This is preliminary. It may not survive further scrutiny. The DESI team themselves were careful to say that the signal is suggestive, not conclusive, and that more data is needed before any claim about evolving dark energy can be made with confidence. The 2024 results are a hint, not an answer. But they matter because if dark energy is evolving, if its equation of state is not a perfect cosmological constant, then every calculation about the long-term fate of the universe needs to be revisited. The timescale of isolation changes, the ultimate fate, freeze or rip or something else entirely, may be different from what the simplest models predict. We do not yet know. We are genuinely in the middle of working it out. And this uncertainty is not a defect, it is the honest state of the science. We have discovered something vast and strange like dark energy, 68% of everything. Only a quarter of a century ago, we are still learning what it is. The question of what dark energy does in the long run is one of the most important open questions in all of physics, and the DESI instrument is actively building the data set that will let us say something more definitive in the years ahead. And there is also this unresolved knot at the heart of modern cosmology, the Hubble tension. The Hubble constant, which measures how fast the universe is expanding at this moment, comes out to around 67 kilometers per second per megaparsec when you measure it from the early universe, from the cosmic microwave background analyzed by the Planck satellite. And it comes out to around 73 kilometers per second per megaparsec when you measure it from the late universe, from Cepheid variable stars and type ET supernovae in nearby galaxies, measured by teams including Adam Rees and the SHIES collaboration. Those two numbers disagree by about 5 standard deviations. In statistics, 5 sigma is the threshold for claiming a genuine discovery. A 5 sigma disagreement between two reliable measurements of the same physical constant is a serious problem, and it has been sitting in the data for years, resisting every attempt to explain it away as a systematic error. It may signal new physics, something in the early universe or in the late universe or in both, that our current models are missing. What that something is, we do not know, but it is a crack in the standard picture, and cracks like this are where new understanding comes from. So we sit, at this particular moment in cosmic history, in a state of remarkable richness. We know so much. The age of the universe to better than 1%, the composition to within a few percent, the structure of the CMB to extraordinary precision, the expansion history across billions of years and we have genuine, serious, open questions. The nature of dark energy, the Hubble tension, the true extent and shape of the unobservable universe, that the best instruments and the most careful minds are working on right now. And all of this knowledge, all of it exists because we happen to live at this moment and not some other. Come back now to the light on its way to us. Somewhere out there, hundreds of millions of light years away, or billion, there are galaxies that are, at this moment in their own frame, going about the business of existing, stars forming, stars dying, quiet nuclear burning on scales we cannot fathom. And some of those galaxies have been sending light in our direction. Some of that light has been traveling toward us for millions of years, or billions of years, crossing the dark between one island of stars and another, carrying information about what those galaxies were like when the light left them. Some of that light will arrive. We will receive it, or our instruments will, and it will tell us something about the universe that we did not know before. And some of that light will not arrive. Some of it left galaxies that have already crossed the event horizon, already receding faster than their own light can overcome. And the light, though still traveling toward us, is in a region of space that is itself being pulled away from us faster than the light can compensate. The distance is growing, not shrinking, even for the photons on their way, and so those photons will travel toward us forever and never arrive. They will be stretched by the expansion until they are infinitely red, infinitely faint, infinitely long in wavelength, until they are, in any practical sense, nothing, not received, not absorbed, just traveling and thinning and fading in a universe that has left them behind. That light is already gone, even though it is still traveling. Those galaxies are already lost, even though their ancient faces are still visible in our telescopes tonight. We are looking at the past and calling it the present, and the truth of their present. Where they are now, what they are now, whether they still exist in any coherent form, is something we will never know and can never know. The gap between what we see and what is has grown too wide, and dark energy is widening it every second. Every second. We used to say that space is between things. Now we understand that space is itself a thing that grows, that has energy, that determines the fate of everything within it. And we are not passive observers of that growth. We are carried by it, bounded by it, ultimately doomed to isolation within it. The observable universe, the event horizon, the Hubble sphere, these are not abstract geometrical constructs. They are the actual limits of our story. But here is what is not lost. Here is what persists. Right now, the evidence is visible. Not just visible, extraordinarily, achingly detailed. The cosmic microwave background printed across the entire sky at a temperature of 2.7 degrees Kelvin carries the fingerprint of density fluctuations from when the universe was only 380,000 years old. Fluctuations so small, 1 part in 100,000, that they represent the seeds of every galaxy and every large-scale structure that has ever formed. We can read that fingerprint. We have read it. The Planck satellite gave us the most precise map of the early universe that has ever existed, and from it we know the age of the universe, its composition, its geometry, its history, with a precision that would have seemed magical even 50 years ago. The most distant confirmed galaxy, JD's GS Z14-0, found by the James Webb Space Telescope in 2024 and reported by Carniani and colleagues in Nature, was there when the universe was only about 290 million years old, a redshift of 14.32, which means its light has been stretched to more than 15 times its original wavelength by the time it reaches us. And still it arrived. Still we caught it. Still we could measure its spectrum and determine what it was made of and when it existed. That is extraordinary. That is only possible because we exist at this moment. The story of the universe, the whole story, from the hot, dense beginning through the formation of the first stars and the first galaxies, and the slow emergence of structure and the acceleration and the approaching isolation, that story is written in the light that is arriving right now, tonight, while you rest. The photons are landing on our instruments and carrying their information and surrendering it to our curiosity, and we are reading it and we are putting it together into a picture that is coherent and beautiful and, yes, a little heartbreaking. And we will not always be able to do this. The trillion-year future astronomer in Milkomeda will look up and see nothing but darkness and one galaxy and draw the wrong conclusion, draw the only conclusion available to them, and live their scientific life in the quiet certainty of a static, eternal, solitary universe. They will not know they are wrong. They cannot know. The evidence for their wrongness will have been swept beyond the event horizon or redshifted into indetectability before any mind evolved to ask the question. We know, we are the ones who know, not because we are special in any cosmological sense, we are not. We are a thin scattering of atoms on a small rock near a middle-aged star on the outer edge of one unremarkable galaxy among hundreds of billions. But we are here, and we are here now, and now is the window. Now is when the light is still arriving. Now is when the CMB is still detectable. Now is when the other galaxies are still visible and their redshift still measurable and the expansion still traceable back to its origin. Now is when you can look at the sky and, if you know how to read it, see not just distance, but time. See the universe getting younger as you look further out. See the evolution of structure. See the afterglow of the beginning itself. There is a particular quality to being in the right place at the right time and knowing it. Not the giddy quality of luck, but something quieter. Something that sits in the chest like a hand pressing gently. We could have been the trillion-year future astronomers born into a void, convinced the universe was always empty and always would be. Instead, we are here, and the universe is here for us to see, and we have the tools to read it and the curiosity to ask what it means. That is not a small thing. So when you think about the edge of the observable universe, when you think about the light that will never arrive, the galaxies already frozen at the event horizon, the tens of thousands of stellar systems per second crossing beyond any possibility of contact, do not think only of loss. Think also of what has not yet been lost. Think of the 100 billion years still remaining in the era of stars. Think of the Milky Way, still forming stars, still pulling interstellar gas into nuclear fires that will burn for millions of years. Think of Andromeda, 110 kilometers per second, closer every second, a future partner, a future merger, a future single great island of light that will persist long after everything else has retreated into darkness. Think of the CMB still arriving, still painting its story across every receiver aimed at the sky. Think of JWST right now catching photons from JD's GS-Z14-0, a galaxy that existed 290 million years into the universe's life, that left its light signature in space 14.32 times the age of its wavelengths ago, and we are receiving it. We are receiving it now. Think of the fact that we are not waiting to be told the universe's history. We are reading it in real time from evidence that will not always exist, in a window that will not always be open. The universe is not static. It never was. And one of the most profound things we have ever discovered, more profound in some ways than any of the individual facts, is that we discovered it in time. Just barely in time. Saul Perlmutter and Brian Schmidt and Adam Rees in 1998 measuring the dimness of supernovae and finding that the universe was not decelerating as everyone had assumed. That was not a comfortable discovery. It was a troubling one. An accelerating universe is a universe building walls, but we found it, and we understood it, and we had time to understand it, and we have spent the quarter century since mapping the consequences. We have time, still, to learn more. The DESI instrument is measuring baryon acoustic oscillations across cosmic history, building a picture of how the expansion rate has varied over time, looking for the signature of evolving dark energy. The Hubble tension is being pulled at from both ends, with next-generation instruments promising tighter measurements of both the early universe and late universe values of HL. The nature of dark energy, a cosmological constant or something stranger, is one of the defining scientific questions of this century, and we are actively right now building the tools to address it. We are not at the end of cosmological discovery. We are probably close to the peak of cosmological discoverability, the window in which the universe is still handing us all of its evidence, and we are spending that window as well as we know how. And beyond the physics there is this. The universe is vast enough that it is almost beyond holding, nearly 100 billion light-years across just in the observable portion, and at minimum 250 times larger unobservable portion. Around that, and beyond even that if the flatness measurements are right, potentially an infinite expanse of space and time and matter and energy and stories we will never hear, civilizations we will never know about if they exist, stars burning in perfect isolation 1 trillion light-years from here, in a region of space whose existence we can infer but never reach, never touch, never illuminate with even a single photon of our own making. All of that, and we are here in one small corner of it, on a rock under a blanket in the dark. And we actually know, not everything, nowhere close to everything, but we know the shape of things, the age of things, the direction things are moving. We know there was a beginning, and that it was hot and dense and small, and that it grew through processes we can trace into the structure we now inhabit. We know there is dark energy and that it is pulling things apart. We know there is a boundary beyond which light cannot reach us, and that the boundary is at 16 billion light-years in co-moving distance, and that it is contracting relative to the matter outside it, and that galaxies are crossing it now, continuously, irreversibly. We know all of this because we are the first creatures in the history of this planet, and perhaps for all we know, in the history of this part of the universe, to have built the instruments and the mathematics to ask these questions and get real answers back. That is something worth carrying into sleep. Not the loss, though the loss is real, not the isolation, though the isolation is coming, but the window, the brief, precious, cosmically unrepeatable window of time in which the full story is still visible, in which the evidence is still arriving, in which the universe has not yet had time to hide what it is and what it was. We were there at the right moment. Not by design. The universe has no design for us, no particular care for our awareness, but by extraordinary accident or extraordinary luck, or simply by the fact that the story takes the time it takes and the questions take as long as they take to occur to beings who can ask them. We arrived at just the moment when the light was still on. Back at the start of tonight, I told you that light was traveling toward you right now. Light that left a galaxy long ago, still crossing the dark, and that it would never arrive. That is still true. But here is the other thing that is true. An enormous amount of light has arrived, is arriving, will continue to arrive for a very long time. The universe is not yet done telling us what it is. We have not yet heard everything it has to say. And somewhere in Milkomeda, 1 trillion years from now, some mind will look at a dark and empty sky and not know any of this. Will not know about the Planck satellite and the cosmic microwave background. Will not know about Saul Perlmutter and Brian Schmidt and Adam Rees and the supernovae that showed the universe was accelerating. Will not know about Abraham Loeb's patient calculations of the long-term future, or Lawrence Krauss and Robert Scherer's quiet, devastating mapping of the knowledge that would be lost. Will not know about the James Webb Space Telescope catching the first light of the first galaxies. Will not know any of it because all of it will have retreated beyond reach, redshifted beyond detectability, lost forever. But we know. Tonight, right now, wherever you are, whatever lamp is still on, whatever sounds are outside your window, we know. We have the full picture, or close to it, and we are still receiving it. The universe is still full enough, still close enough, still bright enough to teach us what it is. That is not a small inheritance, and that is in fact perhaps the most extraordinary thing about the moment we occupy. Not that we are lucky to be alive, though we are, but that we are lucky to be alive now, when the window is still open, when the light is still arriving, when the story of the whole cosmos can still be read in the sky above you. Hold that lightly. You don't have to understand every equation for it to be yours. It belongs to you just by being awake in this moment, in this universe, under this particular sky. If you are still listening, if you haven't drifted off into your own quiet somewhere, thank you. Genuinely. This was a long night's walk through a very large space, and I'm glad you came along. If these slow journeys help you rest, a gentle like or subscribe means more than you might think. Small creators like me really do rely on your support to keep these going. And leave a comment if you feel like it. Tell me where you are tonight and what time it is in your corner of the world. I always read them. I love knowing where the darkness finds you. The universe is still full. Go gently. Good night, kiddo. Grandpa'll leave the porch light on.